In this video, I want to take a look at what it means for two functions to be independent, and then, once we know what it means, how do we decide whether two functions are dependent or independent? Now, the simplest way to describe dependency of two things, this is a concept from linear algebra, and we say that two vectors are linearly dependent if one is a scalar multiple of the other. So they're not independent if one is not a scalar multiple of the other. So from the point of view of vectors, if you think about stuff pointing in different directions, these two vectors are pointing in different directions, they're not dependent. But if they're pointing in the same direction, but maybe one's just longer than the other, so one is just a scaled up version of the other, then they are dependent. Okay. Now, the notion of, if you've had linear algebra, you know that the notion of vectors is much bigger than just arrows. That we think of vectors as anything that behaves like vectors, anything that has the same algebraic properties of vectors. So functions, for instance, are vectors. And I would say that two functions are linearly dependent if one is a scalar multiple of the other. Can you just multiply one by a constant and end up with the other one? And if you can't, then they are independent. Now that's simple enough to say for two vectors, or two functions. But when we get to 3 or 4 or more, which we will in the next chapter, we're going to need to have a broader definition of what it means to be independent. So I'm going to show you, this is the linear algebra definition of what it means to be independent. It's right here. That two vectors, or in this case two functions, are linearly independent if the only way to take a linear combination that adds up to 0 is if both of the coefficients that you're multiplying by are 0. Okay. Certainly if c1 and c2 are 0, then the two functions y1 and y2 multiply c1 times y1 and multiply c2 times y2 and add them up. That's what a linear combination is. Certainly if those constants are both 0, you add up to 0. But is there any other way of doing it? If there is no other way, then they are independent. If you can find a way to get them to add up to 0 where you don't have both of these being 0, then they are called dependent. Now, in the case where y1 and y2 have derivatives, which is the case we will be in because we'll be looking for functions that are solutions to second-order differential equations. So not only do they have derivatives, they're going to have second derivatives. So the functions we'll be dealing with certainly will have derivatives. So the thing is, if you've got this equation, whether c1 and c2 are equaling 0 is the only solution or not, if you know that you've got this adding up to 0, you can implicitly differentiate to get the following here. That just take the derivative of both sides, and you get that c1 y1 prime plus c2 y2 prime is equal to 0. And now I would have two equations with two variables, and maybe I can then solve for the c1 and c2, right? From the linear algebra perspective, I can rewrite this as a matrix equation, where c1 and c2 are my variables, so I put them in this column matrix here, and multiply that column matrix times this 2 by 2 matrix, which is composed of y1, y2, y1 prime, and y2 prime. Notice that the way you multiply matrix, that you take the first row here times the first column, and, well, you do the dot product, right? You multiply this one times that one, and this one times this one, and you add the results, and that's going to be your first entry in the result. And likewise for the second row, first column, doing the same kind of thing. This entry times that entry plus this entry times that entry gives you the thing in the second row, first column of your result. So this matrix equation is equivalent to that system of two equations. In linear algebra, we know that this has a unique solution if the determinant of this coefficient matrix is not 0. If the determinant is 0, then there's more than one solution here. I mean, I know c1 and c2 equaling 0 would be a solution. It's just, is there any other? Is there more than one solution? So determinant equaling 0 would say, yeah, there's going to be more than one solution. Determinant equaling something other than 0 says, no, there's only one solution, which means that those functions were independent. Now, we define this thing called the Wronskian, named after Polish mathematician Józef Wronski, I think was his name. All of a sudden I'm blanking on his first name. Anyway, so we define the Wronskian of y1 and y2 to equal this determinant, the determinant of this matrix. Stick y1 and y2 in the first row of the matrix, and then take their derivatives and stick them in the second row. Now, many of you have had some work with matrices before, but what do we mean by the determinant? The determinant of a 2-by matrix is the product of these two things on this downward sloping diagonal minus the product of the two things on the upward sloping diagonal. So in this case, it would be y1, y2 prime minus y2, y1 prime. That's how I would take that. So let's do a couple of examples. First of all, just the simple Wronskian of x and x squared, or I guess I have it written as x squared and x. So in the first row of my matrix, I'm putting the x squared in the x. Beneath the x squared, I'll put its derivative, 2x, and beneath the x, I will put its derivative, 1. And now I'll take the determinant. So x squared times 1 is that x squared, and then the x times 2x is 2x squared, so I'm subtracting 2x squared, and x squared minus 2x squared is minus x squared. And notice this is not 0. Well, I guess it is equal to 0 at x equals 0, but it's not always equal to 0. For some values of x, it's different than 0. It's not just the constant function 0, right? It is some other function. In the vector space of functions, the function that plays the role of the 0 vector is the function 0, and this is not the function 0. On the other hand, here's one where clearly I've taken x squared and 3x squared, so clearly I'm doing a scalar multiple of 1 to get the other. I'm multiplying x squared times 3 to get the other function, so clearly these are dependent. Notice what happens when I take the Wronskian of these things. So x squared and 3x squared, take the derivatives, 2x, 6x. Now, taking the determinant, the x squared times the 6x is 6x cubed, and the 3x squared times 2x is also 6x cubed, but I'm subtracting, right? It's this product minus that product. So 6x cubed minus 6x cubed is 0. And that is always 0 for every value of x, and that tells me that these two functions are dependent. Now, as I say that, I have to take back, there's a warning. Let me pause. Yes, the Wronskian test is an interesting one in that you only get a positive result one way. So if, like in this first one, the Wronskian was not identically 0, that means that those two functions are definitely independent. With the determinant equaling 0, with the Wronskian equaling to 0, it doesn't mean necessarily that they're not independent. It doesn't necessarily mean that they're dependent. Now, these are dependent. But pick dependent ones, I get a Wronskian of 0. The thing is, you can pick, and they're really obscure functions that you can put together and end up with Wronskians equaling 0, even though the functions are independent. It's like they're dependent on an interval, but not dependent on other intervals. So at least through a particular spot, it might look like the derivatives. Sorry, that this Wronskian is equaling 0, but yeah, let's not worry about that here. What we're going to be worried about is just making sure that we get non-zero, because I know that if I get non-zero Wronskian, the functions are independent, and that's what I'm going to be looking for when I'm solving second-order differential equations. I want to find two independent solutions. Okay. So for instance, let's do one more example here. Sine and cosine. Put sine and cosine as my first row, and I take the derivatives underneath them. So derivative of sine x is cosine x, and the derivative of cosine x is minus sine x. And then when I take the determinant, I get minus sine squared x minus cosine squared x, which is equal to minus 1. And notice minus 1 is never equal to 0. And so these two functions are independent. Okay. Now, we're going to use this to do two different things. We're going to use it to verify that we have independent solutions, and we're going to use it to find a second solution when we only have one.